Now we're going to look at some more interesting examples. So these are polynomials that have some kind of quadratic pattern. They kind of look like the things we've been factoring, but instead of having a straightforward variable like x, they might have something like n plus 3, x minus 2, y minus 4, some kind of binomial. We can still use our same methods for factoring trinomials or factoring a difference of squares. We can either do it as is, just treating the binomial as one term, or we can use substitution to make it look a little easier. So to show you what I mean, for our first example, we have negative 2 times n plus 3 squared, plus 12 times n plus 3, plus 14. And we do kind of notice, it's pretty obvious, we've got an n plus 3 and an n plus 3. It's the same term. We feel like we should be able to factor it out. The only thing kind of stopping us is it's not in the very last piece, but it does show up twice, and we feel like we should be able to factor it out. When we use substitution, let's replace that n plus 3 with another variable temporarily. So we'll say let n plus 3 equal whatever letter we pick. I'm going to go with a capital A. Usually we do see capitals for this kind of substitution. And I'm just going to rewrite my problem. And anywhere there's an n plus 3, I'm going to replace it with a. Negative 2a squared plus 12a plus 14. And writing it like this kind of makes it more obvious. I can already see all three of those numbers are even. I should be able to factor out a 2. For convenience sake, I'm going to make it a negative 2 as a greatest common factor. And in brackets, that would leave me with a squared plus 6a, minus 6a, because I factored out a negative 2. Negative 2 times negative 6a will give me that plus 12a. And similarly, minus 7. Watch the signs on those. And now I have a simple trinomial. A squared minus 6a minus 7. So I want two numbers that multiply to negative 7 and have a sum of negative 6. I'm just using the multiplication sign and the addition sign for product and sum there. Okay, we can stop and list out numbers that multiply, but it's pretty obvious. 1 and 7, we need them to add to negative 6, so it's going to be positive 1 and negative 7. And because it's a simple trinomial, we can factor that as a plus 1 times a minus 7. Notice I'm being really careful to keep that negative 2 in front. It was my greatest common factor. I did factor it out, but it still needs to stay as part of the expression. Now the last thing we do is we say, well, we didn't actually have an a. We had an n plus 3. So let's rewrite the exact same thing, but we're going to put in that n plus 3. I'm going to do it a little lower down so we have enough room. Negative 2 times, instead of a plus 1, that's n plus 3 plus 1. And instead of a minus 7, that's n plus 3 minus 7. But that does seem a little weird. We don't usually write n plus 3 plus 1. We would write n plus 4. Negative 2 times n plus 4. Similarly, we wouldn't write n plus 3 minus 7. We would write that as n minus 4. And there is our fully factored version of that polynomial. So we do see it factored out pretty nicely, actually. Now, performing a little time distortion to check this, because it's not as obvious, let's expand the original polynomial. You can see my work to the right. It's a few steps to kind of multiply it out, but it does eventually reduce to negative 2n squared plus 32. So if I take my factored form, negative 2 times n plus 4 times n minus 4, and multiply it out, it should eventually reduce to the same thing, negative 2n squared plus 32. Let's just check and make sure it does. And thanks to that really convenient difference of squares, the n plus 4 times n minus 4, it's pretty fast to check it, and when we combine our terms, it does work out to negative 2n squared plus 32. So whether we expand our original polynomial or our new factored form, they're equal to the same thing. That's how we know we factored correctly. So our final factored answer is indeed negative 2 times n plus 4 times n minus 4. Now let's take a look at the example on the right. we can use substitution, but we might not even need to for this one. What I'm noticing is I have 4 times x minus 2 squared minus 0.25 times y minus 4 squared. Looking at that first term, we have 4, which is a perfect square, and then we have a binomial being squared as well, the x minus 2 squared. So that first term is definitely a perfect square. What if we look at our last term? We have 0.25, which is 0.5 squared. It's a decimal, but I kind of noticed that 25 anyways. And then I have y minus 4 squared. So again, we have a perfect square. And although we only have 2 terms, we have a difference. So this is actually another difference of squares. Let's do the same thing and take the square root of our first term, the square root of our last term, and see if we can kind of factor this conveniently. So just as a quick reminder, I can take the square root of my first term and the square root of my last term. You'll see them both there below. And then I use that for my binomial, one time where they're being added together, and then a second time with those same 2 terms, 2 times x minus 2, and 0.5 times y minus 4, and this time they're going to be subtracted. So that's actually the base idea behind doing a difference of squares and factoring it. But in this case, looking at it, it does feel like we can simplify, so let's see what we can do. So just kind of multiplying out as much as I can, that 2 times the x minus 2, the 0.5 times the y minus 4. I can see on the left, probably the only thing I can combine is that minus 4 and minus 2. There's one thing I want to point out on the right, and that's the pink text. When I subtract 0.5y minus 2, keep in mind I'm subtracting both parts of that, so I'm actually going to end up with minus 0.5y plus 2. So let's combine what we can in the left and write the right side up. There we go. Now it's not looking all that pretty. We still have a lot of terms, but that's pretty much as we can combine. So our factored form is 2x plus 0.5y minus 6 times 2x minus 0.5y minus 2. Now again, really the only way we can check this is expand out our original and expand out our factored form. We might just do a little more time distortion for that. And thankfully, if we do expand to check, we can see that both our factored version and the original version expand to 4x squared minus 16x minus 0.25y squared plus 2y plus 12. Feel free to just take my word for that unless you really want to do a lot of multiplying to check. Anyways, the important thing to take away from this is 1, be able to recognize that difference of squares, 2, either use substitution or just recognize the binomial in its brackets as one variable, factor what you can, combine any like terms, and there you go.